so this is our Honors Chemistry lesson video. It's part 2 of section 5.3. Alright, so the reason I have this slide up is because we're going to be using this number in our very next problem. So let me go ahead and write it down, because I realize that the question that we start with in this lesson video starts with from the previous question. So here was the answer we got at the end of our part 1 of the lesson video. So it says, if the laser from the previous question, so this was the energy we determined that the photon had in the previous question. So if the laser from the previous question emits a pulse of energy containing 5 times 10 to the 17 photons of this radiation, what is the total energy of that pulse? So when you calculate using your energy formula, E equals h nu, Planck's constant times frequency, that is the energy per photon. So I could literally change my unit to this right here, joules per photon. So in this case, we had the laser emit 5 times 10 to the 17 photons. So if I want to know the total amount of energy, I can just multiply by how much energy one photon has. So 3.11 times 10 to the negative 19 joules per photon. Or you could put per one photon. So see, my photons cancel. Since both my numbers are on top, I'm going to multiply. And once I multiply, I get 0.156 joules. And so that's what I do for that one. So if you know the energy of one photon, and then they ask you the energy of more than one photon, you just multiply by how many photons you have. All right, so let's move on. So you try the next one. Okay, so again, if the laser from the previous question, so here is your energy per photon, emits 1.3 times 10 to the negative 2 joules of energy, how many photons are emitted? Okay, so this time you have the joules per photon, you have the joules of energy, you're trying to figure out how many photons. So I'll let you pause it, try it, and I'll assume you've done that. All right, so this time we're going to start with our joules of energy. So we have 1.3 times 10 to the negative 2 joules. All right, so remember, we're following our golden rule. If I have joules on top, I want joules on bottom. And in this case, it's 3.11 times 10 to the negative 19 joules. And that is the energy of one photon. So my joules cancel. So since one number's on top and one's on bottom, I just divide. So when I divided, I got 4.18 times 10 to the 16 photons. So you can use your energy per photon as a conversion factor. And so then remember, you just determine what goes on top and on bottom based on following the golden rule. All right, so let's move on. So next thing we're going to talk about is a spectrum. Okay, so there's a continuous spectrum, and then we're going to talk about atomic emission spectra. So a continuous spectrum contains light of all wavelengths. So an example would be a rainbow. So if you look, you can see from red all the way to violet. There are no dark spaces where we can't see the color. That is a continuous spectrum. However, when elements create light, so if I pass electricity through a gas or heat something and it creates light, or through a chemical reaction, you don't get a continuous spectrum. You get what we call an atomic emission spectrum. So the atomic emission spectrum is the set of specific wavelengths that are emitted when an element is electrified. The atomic emission spectrum is unique for each element, just like fingerprints are for humans. So for example, you can see here on these, a lot of what you see is dark. It's black. You can't see the colors. But if you look really carefully, I don't know how well it's probably showing up in the video, you can see there's little bands of color. And so those bands of color are showing the movement of the electrons, because those are the specific wavelengths or colors of light that are being emitted by the electron. Every element has its own atomic emission spectrum, just like a fingerprint for humans. So how does this happen? Well, atoms can emit light when you add heat, electricity, or reaction energy. So I can apply heat to it. I can, sorry, I think the next slide has a video that like has a really loud sound, so let me turn that off real quick. I can apply heat to it sometimes, like you can burn elements, that's a flames test. You can pass electricity through it, like in here. You can have reaction energy, like in a glow stick. So the electrons start at ground state. When they absorb energy, they jump to a higher energy level, and that's referred to as excited. So when they're at their lowest energy, it's ground state. When they absorb energy and jump up, they are excited. However, what goes up must come down. So eventually they have to lose that energy and they'll fall back down to ground state. When they lose the energy, some of it is in the form of visible light. So that's where the wavelengths of light come from. So the important thing is atoms emit light when the electrons fall to ground state. Okay, if I ask you about atoms or electrons emitting light, a lot of you want to tell me it's when they gain energy and jump up. That's when they're absorbing the energy. When they lose it, that's when they emit the light, is when they're losing the energy and falling back down to ground state. All right, so this is a video on the next slide. Sometimes it works, sometimes it does not. So we'll just see, whoop, no. If it works, oh yay, it's gonna work. All right, so this is just showing what I was just telling you about. Well, maybe we'll see it, maybe we won't. Well, I'm gonna assume it's not gonna open. So we will move on. All right, so remember how we talked about light has wave properties and particle properties. So remember we said it's like a photon, bundles of energy. They're traveling together. So it's like a beam of bundles of energy called photons. So it's like a light particle that travel kind of like a wave though. So now we're going to talk a little bit about wave behavior, because not only does light act like a wave, matter also acts like waves. So de Broglie suggested that as the electron moves around the nucleus, it is associated with a particular wavelength. So an electron is an actual particle. De Broglie used the term matter waves to describe the wave characteristics of material particles. So he's saying that it's a matter wave when it's an actual particle that's moving like a wave. Okay, for some reason it's not letting me pull it. Okay, so he proposed that the wavelength of any particle depends on its mass and velocity. So what he has here is wavelength equals h, which is Planck's constant, divided by mass. Important note, mass must be in kilograms, and divided by velocity, which is in meters per second. So based on his formula, the wavelength of an object of normal size would be so tiny that it could not be observed. All right, so since Planck's constant is such a small number, if you have a large mass, then that number is going to get even smaller, and so you really can't detect the wave properties of normal sized objects. So when we talk about this, that's why we're focusing on something like an electron, which is very, very small. So its wavelength could actually be detected. So let's look at an example problem. So it says, what is the wavelength of an electron moving with a speed? So this is our velocity. We're looking for wavelength, which is lambda, with a speed of 5.97 times 10 to the 6 meters per second. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. All right, so remember our formula is lambda equals h over m and v. I am solving for lambda, so I don't have to rearrange this formula. Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. And then I divide by my mass, which is in kilograms, so I can use that. 9.11 times 10 to the negative 31 kilograms times my velocity, which is in meters per second. So 5.97 times 10 to the 6 meters per second. All right, so once you solve this, you get 1.22 times 10 to the negative 10 meters. All right, Alright, so just a quick hint here, joules is a kilogram times meters squared per second squared. Alright, so what's happening is this second is going to cancel with our second squared. This second is going to cancel our other second. Our kilograms is going to cancel, and then we would cancel our meters squared, like just the squared part only. So that's how we're left with meters. Okay, so a joule is just a kilogram times meters squared per second squared. If that helps you determine what your final units are, then you can use that. All right, so let's look at another one. So maybe for the next one, pause the video and try it on your own, because you got to be able to do this math. Okay, so I'll assume you've paused it and you're ready to go. So it says calculate the velocity, so this time I'm solving for V, of a neutron whose de Broglie wavelength is 500 picometers. So there's my wavelength. The mass of a neutron is 1.67 times 10 to the negative 27 kilograms. So notice, my mass is in the correct unit. Wavelength needs to be in meters, just like when we use our speed of light formula. Wavelength must be in meters. So let me go ahead and fix that. All right, so I have 500 picometers. We're trying to get to meters, so one step. Follow the golden rule, picometer on top, put picometers on bottom. And remember, one prefix unit equals 10 to the x base unit. So 1 picometer equals 10 to the, and if you look at your, I wish I had one to hold up to you. You should have SI prefixes chart, either that I gave you in class or that you can access on my website to find your powers of 10 for this. All right, so picometers is just 10 to the negative 12, and that's meters. So one prefix unit is 10 to the x base unit. Picometers cancel, and when I solve for that, I get 5 times 10 to the negative 10 meters. So see, this is a number that I can plug in for wavelength. Alright, so remember, our formula is wavelength equals h divided by m and v, but this time I'm solving for v. Now remember, if you're having trouble rearranging a formula, that's something you need to come see me outside of class for. I don't have time to go over that in class. So we don't want to solve for something in the denominator, so the first thing I want to do is get my velocity in the numerator. So see, now I have v wavelength equals h over m. I'm still trying to solve for v, so I divide both sides by wavelength. So in other words, I get v equals h divided by m and lambda, or wavelength. So now I can plug in. So my Planck's constant is 6.626 times 10 to the negative 34 joules times second. My mass is 1.67 times 10 to the negative 27 kilograms. And my wavelength is 5 times 10 to the negative 10 meters. All right, so again, I told you a joule is a kilogram times meters squared per second squared. So let's look at what's going to cancel. So my kilogram is going to cancel, the squared part of meters is going to cancel, and the squared part of seconds is going to cancel. So if you look, I have meters per second left, and when I actually solve, I end up getting 793.5 meters per second, which is the unit for velocity. All right, so for de Broglie, you just got to be careful. Make sure mass is in kilograms. Sometimes they'll give it to you in grams. Make sure wavelength is in meters. You just really have to check your units on that formula. That's about the only thing you have to watch out for. All right, so let's talk a little bit more about some properties of waves. So diffraction is one of the properties that light does that is a wave behavior. And so diffraction is when a wave bends either through an opening or around an obstacle. And so again, that's a behavior of a wave. So a few years after de Broglie published his theory, it was found that electrons, like X-rays, will diffract when passed through a crystal. Diffraction is normally associated with waves. So see again, an electron is an actual particle, but yet it's acting like a wave, like de Broglie predicted with his matter waves. So Heisenberg's uncertainty principle states that when an object has an extremely small mass, like an electron, it is impossible for us to simultaneously know both the exact momentum and location at the same time. If the object is normal size, then the uncertainty would be too small to matter. Okay, so the smaller in mass an object is, the more uncertainty we have if we're trying to identify both the momentum, which deals with speed, and location of an object. But as mass increases, our uncertainty decreases, so we can be more accurate in telling those things simultaneously. All right, so let's look at our section assessment. How are wavelength and frequency of light related? Well, remember, our formula is C equals lambda nu. So C is a constant, 3 times 10 to the 8 meters per second, speed of light in a vacuum. So if wavelength goes up, frequency must go down. Or if frequency goes up, wavelength must go down. So they are indirectly or inversely proportional. And so if you're not going to remember what that means, if one goes up, the other goes down. All right, for number 2, it says describe the cause of atomic emission spectrum of an element. So remember, the atomic emission spectrum is when the electrons release energy in the form of light. So what happens is the electrons gain energy and jump to a higher level. And in parentheses, I'm just going to put excited, because that's what that's called. They become excited. Then they fall back to ground state and release the energy in the form of light. Alright, sorry, that was super long and kind of sloppy, but you know what I mean. It's better than me just saying it to you. Okay, so the important thing, the reason I underlined fall, is because remember, they gain energy and jump up, but that's not when we see the light. When they fall back down to become more stable, they release that energy, and that's when we see the light. Okay, that's when we see the colors, like in the flames test lab, that's when we see the colorful flames. All right, so let's move on to our last couple. Alright, so it says boron atomic number 5 occurs naturally as 2 isotopes, boron 10 and boron 11, with natural abundances of 19.9% and 80.1% respectively. In what ways do the 2 isotopes differ from each other? Okay, remember, isotopes differ anyway by the number of neutrons. So, boron has an atomic number of 5. You can see that on the periodic table. So that means boron 10 has 5 neutrons, whereas boron 11 has 6 neutrons. And then does the electronic configuration of boron 10 differ from that of boron 11? And the answer would be no, electron configuration is the same. Remember, isotopes only differ in number of neutrons, not in number of electrons. So because they're both boron and they're both atoms with no charge, they would have the same electron configuration. All right. So it says draw the orbital diagram. Whenever they say orbital diagram, y'all, that's the same thing as the arrow configuration. Draw the orbital diagram for an atom of boron 11. Which electrons are the valence electrons? Okay, so for boron, we would start at hydrogen. So I do 1s, 1 arrow for hydrogen, 1 for helium. Then I move on to lithium and beryllium, which is 2s. And so I do 1 for lithium, 1 for beryllium. And then I move on to boron, which is 2p. And it only needs, I did a 2-sided arrow there, which looks weird, that match up with my others, which only has 1 electron. So that's the electron configuration, but then it says which ones are valence electrons. The valence electrons are the electrons in the highest energy level, not sublevel. So it's not just the 2p, the 2s and the 2p, because they both are in the second energy level, and that's the highest in this one. Those are your valence electrons. So the 2s and that electron in the 2p are your valence electrons. So then C says, indicate 3 major ways in which the 1s electrons in boron differ from the 2s. Okay, well the 1s electrons are closer to the nucleus. Okay, because as you go in higher energy levels, you get further from the nucleus. A second one would be the 1s electrons have lower energy. Because the energy levels closer to the nucleus have lower energy, and you need more energy to get further from the nucleus. And then the last one kind of goes with this right here. The 1s electrons are not valence. 2s are valence. If it's not valence, we tend to call them core electrons. So we can say 1s electrons are core electrons, and 2s electrons are valence electrons. And you'll just see me abbreviate it VE negative. All right, so that is all for chapter 5. So hopefully you found that to be pretty easy. Main things are electron configuration, all 3 types, quantum numbers, and then learning that math from section 5.3.